Hello guys, in this session we are going to start the next chapter, that is called mathematical modeling of the control system. Of course that is the last chapter. It is the first chapter only, but I said in some flow I left that chapter. Now we are taking that one. Primarily in control system, at very first we are taking some mechanical systems in this universe, but as an electrical engineering point of view I am unable to analyze the properties of mechanical systems. Now we have electrical machine. Electrical machine we have mechanical part as well as electrical part also. But I would like to convert them all into the electrical domain, such that I will get the clear idea about the mechanical systems and electrical systems. Unifiedly you can understand the properties of the electrical as well as mechanical systems. But the thing is, understanding the properties of the mechanical systems in mechanical domain is not a big task. That is, it is a very big task for us, because as an electrical engineer I know all things what to do in electrical domain. So what I am going to do, your control system is going to help us. That is the mathematical modeling especially will going to help us to bring the analogus between electrical domain and the mechanical domain. Actually what is the relations that we are having in mechanical domain and the electrical domain, how to convert any systems from mechanical domain to electrical domain. So that is the beauty of the things that we are going to learn in this system, that is in this session. So the thing is, we are going to take some mechanical systems, of course we are going to consider some electrical systems, and then we are going to bring the relations between mechanical systems and electrical systems. Especially if you see in this universe, mechanically, practical observe mechanical we have some objects outside in this universe. That mechanical object might be a ball at like I have a rotor, so what I can say a bus or what I can say or bus. That bus is going to be moved from one point to another point. That is called a translational displacement. And a tire that is rotating. That is called a rotational, right? So in this universe only two type of objects will be there. Now you can think, either your object might be traveling like this or your object might be rotating. So there are only two type of objects that they are observing mechanically. One is called a translational system and another one is called a mechanical systems. Similarly, in our electrical engineering, that is especially in our electrical circuits, what type of observations that we are getting? Our dissonant circuit either might be connected in, either our circuits might be in series or our circuit might be in parallel. That's all. Yes or no? Of course, we are going to design the combination of series and the parallel circuit. And similarly, if bus whole bus that bus is moving from one point to another point. That is called a translational movement. Whereas if I am looking at the tires are rotating. That is called what I can say rotational movement. So combinedly that bus is working. Bus act. Similarly, in our electrical systems also combination of series and the parallel circuit will going to help us to design the entire network. So the thing is, in mathematical modeling, we are going to see the analogus between mechanical domain and the electrical domain. Especially in mechanical domain, we have two type of systems. One is called a translational system and another one is called a rotational system. Similarly, in electrical domain, we have two type of networks. One is called a series network and another one is called a parallel network. So the difference is, totally we are going to consider four type of people here. One type of people is called a translational, that is these two people that we are going to observe in mechanical domain, and these two people that we are going to observe in electrical domain. Clear? So in mechanical domain, in translational system we are going to observe. See here, even in our electrical domain also we are observing only three people. One is resistor, inductor, capacitor. It might be series or parallel. But now we are going to observe them in the point of our system connection react right? So in electrical system we are going to observe the properties of RLC in series circuit, and we are going to observe the properties of RLC in parallel circuit. Similarly, we are going to observe the properties of, in translational domain we are going to observe three people. One is mass of your body, and another one is damping ratio, that is called a damping coefficient, and another one is we are going to consider spring coefficient. Similarly, in case of rotation also we are going to consider three people. Here in translational system we are considering mass of your body. In rotation system we are considering moment of inertia. Right? So again in translational system we are observing, that is called the damping coefficient. Here also we are going to observe the damping coefficient, but the difference is, here your damping coefficient will be deals with the translation system. This damping coefficient deals with the rotation system. Here also we are going to observe the spring coefficient, but that is called the spring coefficient meant for rotation system. That is, this spring coefficient will be meant for translation system. Or object in one point and the point shift we are applying force. Whereas or object rotate we are applying torque. So the relation between, in translational domain we are going to use force, in rotational domain we are going to use torque, in series circuit we are going to use voltage, in parallel circuit we are going to use current. They are going to act as sources in various circuits, right? The particular is here, that is called force damping coefficient. This is called a torque damping coefficient. This is called force spring coefficient. This is called a torque spring coefficient. Like that, we are also bringing, we will going to see the analogous between these two domains. Once we get the analogous, then what shall we do? For mechanical system namakita irukku sir, but I am unable to analyze the properties of that system in mechanical domain. But now I know, once we get the grip, once we get the relation between mechanical domain and electrical domain, then I can shift the system from this domain to this domain. And then in electrical domain, after getting the mathematical equation, differential equation, we can apply Laplace, we can identify the correspondent poles. Laplace apply panta, adha poles iruka, zeros iruka, types of the system enna, order of the system enna, poles endha location la irukku, system marginally stable ah, unstable ah, what I can say, second order system ah, alla enna systems vandirukku, damping ratio eppadi irukku, k oda value enna irukku, we can put it in root locus, we can draw the Bode plot, we can draw the polar plot, Nyquist plot, you can do anything whatever you want. You can play with your system once you are entering into the electrical domain. So our objective is, whichever the component that I am going to consider in mathematical, that is in mechanical domain, just I am going to shift that things from mechanical domain to electrical domain. That is the one and only thing that we are going to observe in the mathematical modeling. None of the things we are going to do. We are going to see the analogous, that is the relation between mechanical people and electrical people, right? Once we get the relation, then we can shift the people from this domain to this domain. Clear? So let us start the mechanical, that is the relation between mechanical domain and electrical domain one by one. Let us take mechanical system, right? First let us take mechanical translational system. Mechanical translational system, right? In mechanical translational system, totally we are going to observe three people, right? Let me write them directly, right? Totally we are going to observe three people. One is mass of the system, right? First we are going to observe mass of the system, and then we are going to observe the damping coefficient of the system, and then we are going to observe the spring coefficient of the system. Whereas mass of an object will be represented by a box. Let me represent it. This is a box, a small mass, right? A mass. Whereas in case of mass, the force that we are observing, for your mass, the observational force will be F can be written as mass m into d square x upon dt square, right? Right? When the moment we are applying a force on the mass, your mass has to accelerate it, right? It has to be accelerated to move from one point to another point. And that will be decided by the equation, that is m equal to that is F is equal to m into d square x by dt square. That is the amount of force that will be generated from our mass. Similarly, when we are looking for damping coefficient, that is damper, it will be an oscillator, right? There will be some type of vibrations, that are vibrations is keep on contains in our system. That damping will be represented by B, right? So that will be B. When the moment we are applying force on it, right? Correspondent force, right? The force created by the damper is going to be B into dx by dt. That is the amount of force that will be created by the damper. Yeah, guys, this is mechanical system, right? Don't think, sir, because we are not mechanical engineer to analyze all those things. I am just giving introduction. From the mechanical system, if I apply some force, that is how we are getting the equivalent force. We have to convert these things into electrical domain. That is what we are doing here. We are not analyzing the mechanical systems, right? So we are observing, okay, from the mechanical domain, we have some properties, and I am going to shift all those things into electrical domain. Then you can play. In electrical domain, once you get the relation between mechanical domain and electrical domain, then in electrical domain, mathematical equation vandirichadina, and then we can apply Laplace transformation, and then we can identify the correspondent poles, zeros, and you can locate it at wherever you want. You can locate, and you can find out the range of k. You can find out the stability of the system, marginal stability. You can draw Bode plot, polar plot, Nyquist plot. You can analyze the properties of the state space analysis. Whichever the things you want, you can do it. But the primary task is this mathematical, that is mechanical system, will going to be transformed into electrical domain. That is what we want, right? Okay, that is going to be the damper one. And the last we are going to talk about spring coefficient. That is the representation of spring. When the moment we are applying force on your spring, see the development force is simply can be done as k into displacement x. That's all. Clear? K into displacement x. So that is the relation between what I can say damper and the mass and the spring coefficient. When we are connecting these three subjects, that is three objects together, then the net force developed by the system, right? Let us see. I am going to connect these three people together. Very simple, just but we have to understand, right? So mechanically we are observing three people. Like in electrical domain, we are observing resistor, inductor, capacitor. In the same way, in mechanical domain, we are observing three people. Mass, that is mechanical translation system, we are observing three people. Mass, damper coefficient, and spring coefficient, right? So mass will be connected with the, right? In our objective, that object will be, and the object now we are observing three things. One is, and the object move பண்ணும்போது some vibrations will be created, and we have to provide some spring, right? So that is what I can say. I don't want to go in depth. but in that object you can say some spring mechanisms will be there to oppose that is what I can say, and the vibrations accept பண்ணுவாங்க, right? Your machine keep on what I can say create an observer, that is vibration. Under the condition, if I apply any force, that is if I apply any force on the mass, then what will happen? This entire system will experience this force. Under the condition, there will be one opposing force will be created in this side, right? Why? Because we have to balance the system, right? We have to balance the system from the opposition. Like our what I can say, நீங்க பஸ்ல travel பண்ணும்போது pushback seats will be there, na? You can see vibrations will be there, like that. It is going back, getting back, going. That is pushing. That is we are pushing, pulling, right? Such type of observations you can observe from this plane, right? So like that, there are many examples I can explain. No, there is no need. We are in electrical domain. I don't want to confuse you all. Just in mechanical domain, always you can observe these three people. Whenever we are applying the force in a mechanical domain, you can get three people. One is that force will be created. Net force will be force created by the mass, force created by the spring, force created by the damper bar. Right? So net force, that is going to be your total force. Let me connect it with the reference point. Such that the total force can be written as force created by the mass can be written as m into d square x upon dt square acceleration, right? Plus your damper bar, right, will create, that is the relative velocity dx by dt, right? Displacement with respect to time period is called velocity. D square by x over d square is called acceleration, right? Plus at last we are going to discuss about k into x, right? So the thing is, if your acceleration is very high, under the condition, these variations in the velocity and the variations in the spring coefficient are all being neglected. That's why in our electrical machines, when I was talking about rotational machine, I did not consider this effect. In our string equation, I took only this one directly. I hope you all remember. That is for rotational. Now I am going to write. Anyway, just now, right now, remember this expression. Let me write it in a side. M into d square x upon dt square. That is for what I can say, m mass m. And second person for our damper, it can be written as b into dx upon dt. Of course, last person spring can be written as k into x. That is our net force for mechanical translation system. Let us do the same thing for rotational system, right? In rotational system also we are going to observe three things, right? We are going to observe three things. So let me write it here. Now we have to do the same thing for rotational system. In case of rotational system, let me replace mass by moment of inertia J. Why? Now we are going to rotate the object. So it will be represented by, so we are going to observe a rotor, cylindrical, right? Cylindrical rotor. That object is going to be rotated now, right? That object is going to be rotated anyway. In the rotor also you have vibration, no? So we have to vibrational torque will be derived. That is what I can say, vibrational coefficient, right? What I can say now, முன்னாடி நம்ம எழுதின number, that is called force damping coefficient. This is called torque damping coefficient. Because of the torque, because of the force, here we have vibration in our coefficient. That is called force damping coefficient, and here it is called torque damping coefficient. Anyway, it will also be represented by V only. Similarly, here we will have torque spring coefficient, right? So that is how we are keeping our object. Anyway, it will be connected with our shaft and it is going to be rotated now, right? It is going to be rotated such that what will happen? Let me write the relation. When the moment we are applying torque on it, right? When the moment we are applying the torque on it, net torque, first torque developed by the moment of inertia, this body, right? So torque developed by this person can be written as J into d square theta by dt square. I said now the relation. In electrical domain, sorry, in translational domain we have x, displacement. Here we have rotational, it will be represented by theta. That is called angular velocity. That is angular displacement. What I can say, this is displacement, right? Translational displacement, that is angular displacement, right? Okay. Next, what I can suggest, next we have to consider the damper bar, right? So that is called torque damper coefficient. It can be written as b into d theta by dt, right? Just observe the difference. dx by dt linear velocity. Here we have linear velocity but angular velocity, right? That is angular rotation, right? Okay. Plus next spring coefficient k, and here we have displacement from one point to another point, but here we have rotational, so that will be represented by theta, right? So for our rotational system also we are observing three people. One is what? Moment of inertia J, right? Second one is torque damper coefficient. Third one is torque spring coefficient. Clear? So totally we are observing three people on the moment we are applying the torque. So that is going to be net torque that we are observing in our rotational system. Let us keep it in a side. So instead of keeping torque, let me replace it. Sorry, instead of keeping force, this is for translation system. For rotational system, F will be replaced by T and M will be replaced by J. D square by dt square, whereas X will be replaced by theta plus B will be B only. X will be replaced by theta will be dt now K into X will be replaced by theta, right? So that is for rotational system. Let me repeat the same thing for our electrical systems, right? In electrical domain, what we are going to do now, this is all about mechanical system. So in mechanical, we have only two types. One is rotational, another one is translational. In electrical system, for our example, let me take series RLC circuit and parallel RLC circuit just to provide the same relation. For first, let me consider electrical series RLC circuit. Take three people. Electrically, we need three people now. So let me take series RLC circuit. Guys, we can take any combination. But I am just observing the property. Seriously, in series circuit, we have three people: electrical resistor, electrical inductor, electrical capacitor. Similarly, in parallel circuit also. I am just observing the property from them. So when the moment we are connecting all the people in series, let us do it. When the moment we are connecting all the people in series, right? What I am going to do? Let me connect a voltage source here, right? I said in series RLC circuit, applied voltages, that is applied source is our voltage, and it will be shared with all the people, right? So let me assume that is the voltage will apply some current into the circuit. Anyway, here is going to be a resistor, and this is going to be our inductor, and here is going to be our capacitor. Let us write the relation for KVL. KVL. So KVL apply in our room. See, current entering point plus leaving point is minus, entering point plus leaving point is minus, entering point plus leaving point is minus. For our source, current entering point minus, leaving point will be plus. That we know. If a KVL apply V is equal to voltage drop across the resistor can be written as I into R, plus voltage drop across the inductor can be written as V is equal to L into di by dt, right? Plus voltage across the capacitor can be written as what? That is voltage across the capacitor can be simply written as Vc only, right? So this, let me write directly Vc, but we know what you write. That is what you want to write. Capacitor across the voltage that is 1 by C integral of I into dt. That is what we need to do, right? Anyway, so let me replace. Vc if you want to substitute, you can substitute, right? Okay, that's all. So that is the KVL equation for the given system. I said, right? Next, what we are going to do in case of series circuit, right? Anyway, for current expression, we are going to replace. For current expression, we are going to replace dq by dt. For voltage expression, we are going to replace d phi by dt. I said, right? So in case of series circuit, voltage is going to be the source, right? But in series circuit, what I will told you, don't touch a voltage source, because series circuit will be connected with the ideal voltage source. Series circuit will be connected with the ideal voltage source. Whenever if your circuit will be connected with any type of source on the voltage and current on observe panni paapom. What I will told you in my electrical machines, I have been clearly different these things, right? If I am talking about source, voltage source பத்தி பேசுறோம் அப்படினா, your voltage is infinite ideal voltage source. அப்படினா meaning என்ன? You are unable to change the magnitude of the voltage. In voltage source, you cannot change the magnitude of the voltage. In current source, you cannot change the magnitude of the current. So in that point of view, I cannot touch the voltage, but I can change the left current. Because in parallel circuit, I have given the relation, current can be considered as dq by dt. So that relation I am going to consider for series circuit, because I am unable to change the level of voltage. So V can be considered as V only, but I can be replaced by, let me consider dq by dt into resistor R plus L into d by dt into I can be replaced by dq by dt, such that it will become d square q divided by dt square plus 1 by c. See the integral of differentiation. Integral of I க்கு பதிலா dq by dt substitute பண்ணீங்க அப்படினா what will happen? See the இதுக்கு நீங்க integration போட்டீங்க. Let me take integration. I into dt தானே. ரெண்டு பக்கமும் integral of dt போடுங்க. dt getting cancel. So integral of I into dt should be equal to integral of dq. That should be equal to q only. So the net value can be replaced by q by c. Clear? So let me write it in the second order arrangement. See, from this what I have understood, for our series RLC circuit, applied source will be voltage, right? The second order term, first I have to write the second order term, so it will become L into d square q upon dt square s plus second, first order term will become R into dq by dt, right? Plus third term will become q by c. That's all. Clear? So let us continue with this. Okay, let me rub these things. Yeah, let me rub these things. Right? Anyway, that is for series RLC circuit. Let us do the same thing for parallel RLC circuit. Right? Very simple, right? Anyway, already we saw the relations. Any more relations கொண்டு வர போறோம் அப்படிங்கறது already I given. But we have to know the exact relation. Actually, வந்து எப்படி வராங்க, அந்த relations எப்படி வருது அப்படிங்கறது we have to know. Whether we are taking reciprocal or அப்படியே வருது அப்படிங்கறது linear relations. But I have given the general relation. எப்படி வரணும், யாரை கன்சிடர் பண்ணனும்னு நான் சொல்லிட்டேன், right? Let us see. Finally, we are going to consider parallel RLC circuit, right? Parallel RLC circuit. Let us see. In case of parallel RLC circuit, we are going to consider once again resistor. Yeah. then we are going to consider inductor, and then we are going to consider capacitor. All the people are going to be connected in parallel with the parallel current source, right? So in case of parallel circuit, I said current is going to be your source. Now tell me, can you change the magnitude of the current? No. But I know I have to consider either I can be replaced by dq by dt or v can be replaced by d phi by dt, right? D phi by dt. But in series circuit, we were connecting infinite ideal voltage source, so I was unable to touch this one. I touched current. In parallel circuit, current is going to be infinite ideal voltage source, so this relation is invalid here. I cannot touch the value of current, but you can replace it, right? You can use the second relation. I am going to use voltage relation. Let us see. For that, I am applying KCL here. Let us apply KCL. If I will apply KCL, there are three branches. Net current should be equal to current taken by the resistor. Let me consider IR. Current taken by the inductor, let me consider IL. Current taken by the capacitor, let me consider IC. Such that the value of current, net current can be written as IR plus IL, that is vector addition, plus IL plus IC, right? Shall we write it further? Yes. Current will be, see, let me take, in the Mottaman net circuit voltage on V again, right? Across the current source, and here I am going to consider voltage, same voltage, same voltage. Why? All the people are connected in parallel circuit, voltage will going to be same. For all people, right? If there is any change, current voltage say there's no change. If you get 10, I'll add 10. In the 5, I'll add 5. In the 3, I'll add 3. So let us continue with that. So let me fix I itself. Current to the resistor can be written as I is equal to V by R according to Ohm's law. Voltage drop across the resistor is V, supply voltage divided by resistor. Same voltage will be dropped to all people, right? Across the all people. Inductor will current for inductor it can be written as 1 by L integral of V into dt plus for capacitor I is equal to C into dV by dt. That relation we know. Let us continue further. I said just replace V by d phi by dt, right? I said V is equal to d phi by dt. Up and over. Finally, current equation I can be written as simply it can be written as, first I will take this term because I would like to arrange in the second order first term and then zeroth order. Second order term it will become here C into, let me substitute d square phi by dt square. How it is can here? See that V will be replaced by d phi by dt such that it will become d by dt into d phi by dt will become d square phi by dt square plus, and then we have to consider the first order term, so let me take this one. V will be replaced by d phi by dt such that it will become 1 by R into d phi by dt plus, so last term I will take this one 1 by L into, see that, let me take integral on both sides, integral with respect to dt, integral with respect to dt, so dt getting cancelled, integral of d phi should be equal to 5 only now, so integral of V into dt, integral of V into dt will be replaced by 5, so this whole term will be replaced by 5 such that it will become 5 by L. So that is the actual relation between mechanical domain and the electrical domains of the various systems, right? So let me make the box once again such that you will get the clear idea. Already what I have done, just I have given the relation. Let me take the mechanical system once again. Just to remember these four equations. Mechanical system, in mechanical we are going to consider translation system and then rotational system, and then we are going to consider electrical domain. In electrical domain we are going to consider series RLC circuit, and then we are going to consider parallel circuit. Let us see the relations between various people. When I am looking for mechanical system, in mechanical system the source here, force is going to be our source. For rotation system, torque is going to be our source. For series circuit, voltage is going to be our source. Parallel circuit, current is going to be our source. Similarly, if I write the relation, see there, in mechanical system, mass of the body can be written as m, right? For electrical system, it is going to be, rotation system, it is going to be J. For electrical, that is for inductor, for series circuit, J will be replaced by L, that is going to be mass. For parallel circuit, that is going to be C, equivalent values. Similarly, when I am looking for what I can say, damper coefficient, right? So for force, damper coefficient can be written as V. Rotation system, that is also going to be same V. Just to compare, second order its correspondent coefficient, first order its correspondent coefficient, zeroth order its correspondent coefficient, so you will get the answer, right? So like that, if I write the expression for here BBR 1 by R, BBR 1 by R, let us see spring coefficient KQ5, right? So it is going to be K, let me consider Q, here I am going to consider 5, that is going to be spring coefficient. At last what we are going to do, let us consider, right? And similarly, see that here I am considering displacement x, and here I am considering displacement is theta, and here they are considering displacement is q. Sorry guys, here I made a mistake, sorry. See what I have done, k coefficient is k, here it is k, here it is 1 by c, no, sorry, here it is 1 by c, where I have written like this one, k, so here it is 1 by c and here it is 1 by l, sorry, here it is 1 by l, that is what I have been told you, right, that I just, I was written the equation, here we are going to consider the effect of capacitor, here we are going to consider the effect of inductor, but we have to take reciprocal for them, right, why, because this relation, see there, this is my spring coefficient, force spring coefficient, torque spring coefficient, voltage correspondent coefficient, current correspondent coefficient, right? So that is going to be what? K 1 by C 1 by L. Actually Q phi are the displacement, right? Series circuit நம்ம யாரை மூவ் பண்ண போறோம்? See, ஒரு மெக்கானிக்கல் டொமைன்ல டிரான்ஸ்லேஷன் அப்படினா டிஸ்பிளேஸ்மென்ட் x ஒரு பாயிண்ட்ல இருந்து இன்னொரு பாயிண்ட்க்கு நீங்க எவ்வளவு டிஸ்டன்ஸ் வந்து மூவ் பண்ணிருக்கீங்க. அதே மாதிரி ரொட்டேஷன்ல θ எவ்வளவு ஆங்கிள்ல ரொட்டேட் பண்ணிருக்கீங்க. In electrical series circuit charge எவ்வளவு சார்ஜ் வந்து நம்ம மூவ் பண்றோம். In parallel circuit we are considering phi, variation of phi, right? So let us continue. So that is going to be what? X theta q, that is going to be phi. That is the actual table column, right? Just to make a very clear notes, right? Yes, that's all. So that is how we are bringing the relation between various domains. Guys, don't forget, because these relations are very, very important in our exam point of view. You will be tested often, right, from this relation. Just I have been told you now, just you have to bring the relation. For force க்கும் voltage க்கும் என்ன relation தெரியும். இங்க m னா இங்க என்ன relation தெரியும். இங்க b னா இங்க என்ன relation தெரியும். Like இங்க x அப்படினா இங்க correspondent relation என்ன அப்படினு தெரியும், right? Just you have to remember this relation. So that is all about mathematical modeling of our control system. So நம்ம என்ன பண்ணிருக்கோம், just I took some mechanical systems. I had given the relations between mechanical domain and the electrical domain, right? So at the beginning I had given some relations, but I did not wrote C, L அப்படினா எழுதல, right? Just now I got the correct relations, just to remember. Why I have written that one? Just for friction, right? Now you don't need to memorize, guys. You don't need to memorize. Just to should try to understand. நீங்க இப்ப நான் பாருங்க இதெல்லாம் நான் memorize பண்ணேன். No, I did not memorize anything, but I know how to derive these things. Sir, exam la பாதிக்காக பண்ணிட்டு இருக்க முடியுமா? I am not telling like that, right? Once you understand these things, it will be registered into your mind, right? ஒரு series circuitல inductors ஒரு டைம் நீங்க ரெஜிஸ்டர் பண்ணீனா automatically remaining things will fall in place. See that இங்க டேம்பர் பார்க்க ரெசிஸ்டர் தான் எப்பவுமே வர போகுது. இங்க ரெசிஸ்டர் இங்க கண்டக்டர். அதே மாதிரி இங்க மாஸ் சீரியஸ் சர்க்யூட்டை பொறுத்த வரைக்கும், ரைட், எலக்ட்ரிக்கல் சர்க்யூட்ஸ்ல சீரியஸ்னா மாஸ் வந்து இண்டக்டர், அப்ப பேரலல்னா ஆப்போசிட் கெபாசிட்டர் வந்துரும். அதே மாதிரி இங்க சீரியஸ்னா வந்து இப்போ இங்க இண்டக்டர் அப்படினா அது இண்டக்டர் வந்து இங்க மாஸ் ஆக்ட் ஆயிட்டு அப்படினா ஸ்ப்ரிங் வந்து கெபாசிட்டர் ஆக்ட் ஆகும். அதே மாதிரி இந்த இடத்துல parallel circuitல கெபாசிட்டர் மாஸ் ஆக்ட் ஆயிட்டு இருக்கும்போது இண்டக்டர் will act as a spring coefficient, but we have to take reciprocal, that's all, right? So just remember this relation. That much of knowledge is sufficient to crack all the questions from the mathematical modeling of the control system. I hope you all have understand. Just you should try to make very notes, that is very clear notes. At last, that is before going to the exam, make what I can say ஒரு டைம் வந்து ஃபுல்லா ரிவைஸ் பண்ணிட்டு and then go and try it in the examination. Definitely I hope you are going to get the answer. Thank you all.